Welcome to Lecture 5.1, Fourier's Law and the Diffusion Equation. This is the first lecture on partial differential equations. Let's begin by considering a two-variable function u of x and t, so that's position and time. A partial differential equation, or PDE, is an equation involving the function u and the variables x and t and the partial derivatives of u. Now, though this definition is just for a two-variable function, it should be clear how this generalizes to functions of more variables. Next, let's say a few words comparing PDEs and ODEs. As we've seen, ODEs have a unifying theory of existence and uniqueness of solutions. In particular, if we have a linear homogeneous nth order ODE, then the general solution is a vector space of dimension n. Moreover, if we have n initial conditions, for example, we have y of 0 and y prime of 0, y double prime of 0, all the way up to the n minus first derivative at 0. If we know all of these values, then we have a unique solution. As we've seen, things are a little bit trickier if we have a boundary value problem instead of an initial value problem, but the point remains that PDEs have no such theory. PDEs arise from physical phenomena and modeling, which is why they're so important in mathematics, science, and engineering. That, along with the fact that there's no unifying theory of their solutions, just underscores how massive of a challenge current research is in PDEs. People have to do things like look at special cases of equations, or solve them numerically, or run massive computer simulations to get insight, especially when these are modeling intricate real-world problems with lots of parameters and lots of bells and whistles. What we will do in this class is look at some of the basic PDEs, things like the heat equation, the wave equation, and Laplace's equation, which form a fundamental basis or foundation for the theory of PDEs. We'll begin with the diffusion equation, which is a PDE that can model the motion of a number of physical processes, such as the diffusion of smoke in the air, the diffusion of dye in a solution, or the diffusion of heat through a medium. We'll begin with a three-dimensional example of this because we live in the three-dimensional world. Let's let u be a function of x, y, and z and time t. Let that represent the concentration of smoke or dye, or if you prefer, the temperature at position x, y, z and time t. Let f be the vector field that describes the flow of smoke, or dye, or heat, or whatever material we're looking at. Our goal is to relate how the concentration u varies with respect to time to how it varies with respect to space. So this first one is just du dt, and how it varies with respect to space, that involves du dx, du dy, and du dz. Not just first derivatives, but could be second and third, and so on. I'm going to give you the definition right away, and then I'm going to spend much of the first part of this lecture justifying where it comes from. So think of this as a physical law, sort of like Newton's law of cooling. The diffusion equation, or the heat equation, is the following PDE. So it's du dt is k times the Laplacian of u. Remember what the Laplacian is? Recall what this del squared is. That's the product of the del operator with itself. And here the del operator is the vector of partial derivative operators, so d dx, d dy, and d dz. And I want to specify that even though u is a four-variable function involving x, y, z, and t, whenever we see things like the Laplacian of u, we're only looking at the spatial variables. So that's an important distinction to make. So now del dot del, or del squared as it's written, is just the sum of the second derivative operator. So it's del squared, or d squared dx squared plus d squared dy squared plus d squared dz squared. And in general, if you recall from vector calculus, del times f for some function f is just called the divergence of f. So this is equal to k times the sum of the second spatial derivatives of u. We'll usually write that as k times uxx plus uyy plus uzz. So this is what it is in 3 dimensions, and it's easy to see what it is in 1 dimension. If we just have x and t, then this equation is ut equals a positive constant k times uxx. So that's the heat equation in 1 dimension. And even though I'm introducing it to you here in 3, most of the stuff that we're going to do in this section is going to be solving the 1-dimensional equations. Later in the course, we will look at 2- and 3-dimensional solutions. I want to spend the next few slides justifying where that equation came from. It's basically 2 things put together. One of them is Fourier's law of diffusion. This is from physics, or from common sense. And the second one is the divergence theorem from vector calculus. So let's start with Fourier's law. This just says that material flows from regions of greater to lesser concentration at a rate proportional to the gradient. So mathematically, that says that the vector field F, which is the direction of the flow of smoke or dye or heat, or you can think of it in other contexts. It might be a forest fire, and it's pointing to the direction that the fire is spreading the fastest. And I'm sure we can come up with other examples. So when I say rate proportional to the gradient, that means F is equal to negative K times del U. Here are some pictures of this. In the first one, imagine this being the concentration maybe of some dye in a pipe, and that's going to spread out in both directions. Or maybe you prefer to think of this as the distribution of heat in a bar. So it's hottest in the middle, and the heat will spread out left and right. Or physically, you can think of this as a pile of sand, and then there's grains everywhere that are going to roll down the hill. And the grains of sand at the top, near the top, are not going to roll very fast because it's not very steep here. And at the bottom, they're not going to roll very fast either because it's not very steep. But in the middle, this is where it's the steepest. Those grains of sand are going to start rolling faster than they do at the top or at the bottom. Here's a 2D example of this. So you can picture this contour map either as being maybe that sand pile, or as being maybe a temperature gradient. So everything along this line is the same temperature, and the temperature is going to spread out, the heat will spread out in the direction perpendicular to these contours, and it's going to spread out faster where it's steeper. There are basically 2 steps involved to deriving the diffusion equation. The first one is to start with Fourier's law, which is what I just showed you, that the vector field F is negative K times the gradient of U. So this relates the vector field with the spatial derivatives of U, how the concentration is changing over space. Next, we relate F with the rate of change of concentration with respect to time. And we do that with the divergence theorem. And you might be rusty on the divergence theorem, and that's fine. Let me recall that the divergence of F measures the rate of expansion of F at any point in time. So this says that if we integrate that expansion over the solid region D, let me sketch it something like this. So we're adding up how much heat is being created inside, or smoke or dye, like we're adding up the sources minus the sinks, then we can just measure that by taking the flux of the vector field through S, and S is the boundary. So the boundary of D is S. So what this looks like is maybe the vector field looks something like this. And so at any point, we take the normal vector n, and we take F, and we take the dot product of F in the direction of n, and that's how much of F is passing through at that point. So this is the divergence theorem. It says that if you add up the divergence throughout the whole region, that's just equal to the flux through the surface. So how much smoke or dye or heat is passing through the surface, and that's given by this double integral. So we know by the divergence theorem that this triple integral here represents the amount of smoke or dye or heat that flows through S per unit time. But another way to measure that is to take the total amount of our quantity, whether that be smoke or dye or heat, that's obtained by just integrating the density function over the solid region, and then looking at the rate of change of that amount. So that's taking ddt of this triple integral. And we need a negative sign because when the flux is positive, that's when our quantity is exiting the surface. Now, this integral is with respect to x, y, and z position, and so we can just move this ddt inside and attach it onto the u. So this is just negative times the integral of du dt over the whole region D. And that holds for any region. In other words, since the integral of the divergence of f equals the integral of negative du dt over any region D, then those things must be the same. In other words, the divergence of f has to be equal to negative du dt. Now, all that's left is to take this equation that we just derived and plug it into Fourier's law. And that's all there is. So negative du dt, which is equal to the divergence of f, and by definition, the divergence of f is del dot f, and we have an expression for f by Fourier's law, and that's del dot negative k times the gradient of u. So we can pull the negative k out of here. This negative sign cancels with that negative sign, and write this as k del squared u. In other words, du dt equals k times Laplacian of u. So that is the derivation of the diffusion equation. Notice that in one spatial dimension, this PDE reduces down to the following. Du dt equals k times d squared u over dx squared, or I'll usually write this as ut equals k uxx, just because that's simpler. Finally, it's worth mentioning that in this derivation of the diffusion equation, we were assuming that there was uniformity to the medium that the quantity was diffusing through. For example, if it was through air or through water, then we were assuming that the diffusion coefficients are constant throughout. And if we're looking at the heat equation, then we're assuming that things like the density or the specific heat of the bar or the thermal conductivity, those things are all constant. Now that need not be the case. It is in many, many cases, like dye going through water. But there are cases when those quantities change. So it's worth at least mentioning how these equations change in the non-uniform case, as I like to call it. So let's only look at the one-dimensional case. So first, for diffusion, suppose we have a pipe of length L containing a medium such as water, and we're looking at maybe a chemical in the water. Then the diffusion equation is the following PDE. So du dt on the left is just ddx of capital D of u and x times du dx, where, as before, u is just the density of the diffusing material at position x and time t. And now capital D is called the collective diffusion coefficient, and that could depend on the density of the material and on the position. We're assuming it's not going to depend on time. We're assuming that at least the medium is not changing over time. If we assume that this diffusion coefficient is constant, then the diffusion equation reduces to what we saw before. So ut equals, I'm going to call it c squared uxx, and c squared equals negative d. So before we had k, I like to write this as c squared for two reasons. First of all, to emphasize the fact that it's positive, but also because, as we'll see soon, we're going to see a lot of other letters like n squared, pi squared, l squared, and it's just convenient to have a c squared. Similarly, for heat flow in one dimension, in the non-uniform case, suppose we have a bar of length L that is insulated along its interior, so heat flows only in one direction. Then the heat equation in general is the following PDE. So it's rho of x times sigma of x times du dt times ddx of kappa of x times du dx. And that's horribly messy, but let me just mention what these quantities are. So U is the temperature of the bar, of course, at position x in time t. Rho of x is the density of the bar at position x. Sigma of x is the specific heat at position x. And kappa of x is the thermal conductivity at position x. As before, it's not at all a bad assumption that the bar is uniform. It typically is. I mean, metal bars, unless they're alloys and they go from copper on one side to brass to the other side, we're going to assume that things like rho, sigma, and kappa are constant. In this case, the heat equation is just UT equals C squared UXX. And here, C squared, if you solve for it, is just kappa divided by rho times sigma. Now that we've seen where the heat equation comes from, I want to add boundary and initial conditions. And I really want to emphasize throughout these lectures how this matches up with modeling the actual physical situation. This is best done with an example. So this is example 1a. We'll also do examples 1b and 1c and 2 and 3 and maybe more, but these will be spread throughout multiple lectures. This is the only example that we'll be doing in this lecture. So the following is a boundary and initial value problem. So I will write this as B/IVP or some permutation thereof, maybe I/B or maybe BVP/IVP, for the heat equation in one dimension. So this is the heat equation, UT equals C squared UXX. Here we have two boundary conditions and one initial condition. So I want to talk about what this models, and I'll go over these boundary and initial conditions one by one. So first of all, consider a bar of length L. So the left endpoint we're going to say is x equals 0, and the right endpoint is x equals L. And this bar is insulated along the interior, so heat just travels in one dimension, laterally. Now these boundary conditions tell us what the temperature is going to be fixed at the boundaries. So this first one says the temperature at position x is equal to 0 for all time t. So imagine we have an ice bag here and we fix this to be 0 degrees, and then the right endpoint is x equals L, and this boundary condition says the temperature at position L is also equal to 0 for all time t. So we have an ice bag here as well. Now another way to think about this is this pipe is insulated along the interior, but not at the endpoints. So it's cut open and exposed at the endpoints, and it's sitting in a room whose ambient temperature is 0 degrees. That might be a little more realistic than sticking bags of ice here. So these are boundary conditions, because we're specifying what the temperature is at the boundary of the bar. And finally, we have an initial condition. This tells us what the temperature is initially at time equals 0. So at time equals 0, we take a snapshot and we say the temperature as a function of x at t equals 0 is this function x times L minus x. Now I've picked this function because we've seen it before, and it is this upside down parabola that looks like that. So this is the graph of the temperature of the bar. So its hottest point is in the middle. So this is U of x0 equals xL minus x. And so at time equals 0, this is what the bar looks like, or the temperature anyways. Now what's going to happen over time? Just think about this intuitively. We got this bar that's hot in the middle, cool toward the outsides, and it's uninsulated at the endpoints. So a few minutes later, this bar is going to look, the temperature is going to look like that. It's going to be diffusing. And a few minutes later, it's going to be flatter and flatter. And then what do you think the limit as time goes to infinity of the temperature of the bar is going to be? Well, hopefully, just using your physical intuition alone, you realize that it's going to be 0 degrees, that all of the heat is going to escape throughout the bar. And that's what heat does. It diffuses. Now let me change up these initial conditions here. I'm going to give you a picture of a much more wild initial condition. And that's this graph right here. If this represents the initial temperature of a bar, then as time goes on, this temperature spreads out and spreads out and spreads out more, and for larger time becomes very flat. Now I should point out that in this particular case, at x equals 0, the temperature is not actually 0. So while this represents an instance of the heat equation, it does not represent this particular instance of the heat equation. There's something else going on at the boundary, some other boundary condition, and we'll learn more about that in the next lecture. For now, I want to finish by pointing out that we have one time derivative here and one initial condition, and two spatial derivatives and two boundary conditions. And that is not a coincidence. Turns out that this is exactly what we need to specify a unique solution for temperature. And we'll understand that both mathematically and intuitively in the next few lectures. But think of this as analogous to what we know from ODEs, or just basic calculus. If you have an equation like x prime equals negative 9.8 t, might represent the position, or the velocity, I should say, of a falling object, then if we want to solve this, we have to integrate both sides, and we get a constant of integration. So we need an initial condition, say the initial position, x of 0 equals x naught, to completely specify a solution. In contrast, if we have a second order equation like x double prime equals negative 9.8, then we need two initial conditions. We need x of 0 equals x naught, the initial position, and x prime of 0 equals, say, v naught, the initial velocity. So as before, for each derivative, we need an initial condition. Same thing here, but for time derivatives, initial conditions. Spatial derivatives, boundary conditions. We will finish this lecture by solving the PDE in example 1.a. Now PDEs, like ODEs, can be homogeneous or inhomogeneous. And like ODEs, we will solve them by first solving the related homogeneous equation, if the PDE is inhomogeneous. Next, by finding a particular solution, which in this case will almost always be a steady state solution. Anything else is just way too hard. And finally, we just add these two solutions together. So it's really just like what we're doing for ODEs. Most common homogeneous PDEs can be solved by a method called separation of variables. Sounds familiar. It's a lot like what we do for ODEs, but obviously more complicated. Here's a summary of how the method works in one dimension. So consider the following PDE, same one that we saw before. We first will assume that there is a solution of the following form. U of xt equals f of x times g of t. So a function of position times a function of time. We're not assuming that the general solution is like this, but we're just assuming that there is one, and we will find it. We plug this back into the PDE, so we take derivatives and plug it back in for ut and uxx, and we solve for f of x and g of t, basically by putting all the x's on one side and all the t's on the other side. It's called separating variables. What we'll get is we'll get a boundary value problem for f of x and an ODE for g of t. These are things we can solve, and what we'll get is we'll get a solution un of x and t for each integer n. So for each n, we'll get a particular f of x and g of t. By superposition, which is the physical term for linearity, if we have a collection of solutions un of x and t, then any linear combination is a solution. So the general solution is potentially an infinite sum over all integers 0 to infinity of Cn un of x and t, where Cn can be any constant. Finally, we will use the initial condition to find the Cn's. So we're going to plug in 0, and we will get, turns out, a Fourier series. And then we'll have to write this initial condition in a Fourier series. And then we set the corresponding coefficients equal. Okay, let's do this. Here's that example 1a from before. So the first thing that we always do is we assume that there is a solution, u of x t, of the form f of x g of t. And we will plug this back into the PDE. So before we can plug it in, we have to take derivatives. So ut, the time derivative, is just f of x g prime of t, because with respect to t, f of x is just a constant. And similarly, uxx is just f double prime of x times g of t, because with respect to x, g of t is a constant. So now we are going to plug these things back in. So the left-hand side is ut, which is f times g prime, and that equals c squared times uxx, which is f double prime g. Now there's several things you can do. You want to put all of the x's on one side and all of the t's on the other side. Here's what you should always do. Here's the best way to do that, is what I mean. Divide both sides by c squared fg. So remember that, c squared fg. If you do that, then on the left-hand side, the f's will cancel. And on the right-hand sides, the g's and the c squareds will cancel. And what you'll get is g prime over c squared g equals f double prime over f. Now you could keep the c squared along on this side with the f's, but this is a simpler ODE because there's only one derivative. So keep the constant on that side. Okay, so now what do we have? We have this equality. On the left-hand side, this is a function of time and only of time. It's g prime of t over g of t. In other words, it does not depend on space at all. And it is equal to this quantity on the right-hand side, which is only a function of position, of x. In other words, this does not depend on time. So what if I told you that I had a quantity that does not depend on position or depend on time? You would tell me that that has to be constant. So I'm going to set that equal to lambda. And let me just specify, so let me just write here that this doesn't depend on position, x, and this is equal to something that doesn't depend on time, t. So just imagine that I said the temperature in this room does not change with time or doesn't change with space. You would of course say it's constant. Okay, so I'm going to set that equal to a constant lambda. And I'm going to put a negative lambda in front, and you'll see why shortly. It doesn't really matter. Not something you have to do. So what does this tell us? Well, this tells us that we actually have two equations. One of them we set the g's equal to lambda, and then we set the f's equal to lambda. So the first equation we get is that f double prime equals negative lambda f. And the second equation is g prime equals negative c squared lambda g. So now we have two ODEs. Now I should mention that at this point we can actually derive boundary conditions for this ODE and f from the boundary conditions given in the PDE. And let's do that now. So I'm going to go over to the right-hand side here, and I'm going to show you how to do this. So let's do these boundary conditions one by one. And here's how I like to think about this. Anytime we have a boundary or an initial condition that's equal to 0, we should use those things right away. So and I call those 0 boundary conditions. Let me write that up. 0 boundary conditions. So what I'm going to do is I'm going to write that u of 0 and t. Now, what is that? remember what u is. U is f times g. So u of 0 and t is just f of 0 times g of t. And that's equal to 0. So we have a function g of t. Oh, by the way, f and g clearly have to be non-zero because initially they're non-zero. So g of t is not the zero function. But we have this number, f of 0, times a function that's equal to 0. So that number has to be equal to 0. So we conclude right away that f of 0 equals 0. And that's important. Let me box that. Similarly, we have this other boundary condition. This says that u at L and t, well, as before, let's just plug in L into f of x. So u of L and t is f of L times g of t. Once again, that's equal to 0. And we have a number times a function g equaling 0. The only way that could happen is if that number, f of L, was equal to 0. So that's our second boundary condition. So what we get is with this ODE right here, that looks like a Sturm-Liouville equation, it is a Sturm-Liouville equation. We can add the boundary conditions f of 0 equals f of L equals 0. So now we have this here is a boundary value problem. It's a Sturm-Liouville equation. And the second one is, it's just a regular ODE. We don't have any initial conditions. We have an initial condition here, but my rule of thumb is you can only use them early if they're equal to 0. So this is not equal to 0. We will have to use this thing later. Okay, let's solve these. Well, we've done this. This first equation, we solved this in the last series of lectures on boundary value problems. And recall what the solution was. So lambda was equal to n pi over L squared. Remember that? Go back and look at, I think it's lecture 4.1 if you don't remember how to do this. You need to know how to solve these things. So that's what lambda was. And I'm going to call that lambda n because we get one for each n. And the solution, fn of x, if you remember, was sine of n pi x over L. So there we go. We have found f and we found lambda. Now let's solve for g. So g prime is negative c squared lambda g. We know what lambda is now. It's n pi over L squared. So this is equal to negative c n pi over L squared g. So in other words, g prime equals this. And that's just exponential decay. G prime equals negative kg. We know how to solve that. I mean, it looks like a complicated constant, but remember, that just means that g, I'm going to say gn of t, because this depends on this particular n. This is just e to the negative, that constant. So that's cn pi over L, quantity squared, times t. And, you know, I could put a constant in front of here if I want to. For these equations, I don't actually need constants. A constant will come later. So even though the general solution, yes, has a c here, we don't need that. Because all we want to do is we want to find a solution. And we found one. We found f, and we found g. So now our solution is for each n, and I'm going to say starting at 1, 2, 3, etc. Now if n equals 0, we get sine of 0 is 0. So yeah, we get a 0. It doesn't tell us anything new. And similarly for negative n, again, this boundary value problem, we only get non-zero solutions for positive integers. Or if we have negative integers, we don't get anything new. We get the same solution up to a negative sign. So we can assume that n is a positive integer. We get a solution un of xt equals fn of x gn of t, which is just the product of these two things. So that's sine of n pi x over L times e to the negative cn pi over L squared t. So here is a solution, and we get one of these for every integer n. So by superposition or by linearity, if we have a solution like this for any n, then any linear combination of those are solutions as well. So now, by linearity, the general solution, and when I say the general solution, I'm going to say the general solution to this boundary value problem. Not the initial value problem yet, just the boundary value problem, because I haven't used the initial condition. So together, this is a boundary value problem. So by linearity, the general solution to this BVP is u of x t is the infinite sum from n equals 1 to infinity of c. I'm going to call it bn because we have signs. Bn times un of x t, which is just the infinite sum from n equals 1 to infinity of bn sine of n pi x over L times e to the minus cn pi over L squared t. So this is our general solution. It physically represents every single solution to the heat equation. So the heat equation is at this bar here. Given the fact that the endpoints are fixed at 0 degrees, and saying nothing about the initial condition just yet. So any sort of initial condition that we want to give can be described like this. Here is a summary of what we just did. Now we're going to use the one thing that we haven't done yet, and that's use the initial condition. And we're going to do this just like we always do it. We plug in 0 to our general solution and set it equal to the initial condition and solve for the coefficients. Okay, let's do it. So let's take u of x and 0, so t equals 0, and look what we get. We get n equals 1 to infinity, bn sine of n pi x over L times e to the 0, which is 1. And we have to set that equal to our initial condition, which is equal to x times L minus x. Now, this is a sum of sine waves, and this is a polynomial function. Remember, what this looks like is something like that. So those aren't equal. But we don't need them to be equal everywhere. We only need them to be equal on 0 to L. So how do we do that? How do we set a function equal to a Fourier sine series? Well, I just said it. You compute the Fourier sine series of this function. So you take this little signal right here, this little piece, and you make it odd. There you go. And then you compute the Fourier series of the odd extension of that. So this function right here. And we've actually done this for this particular function, or almost this particular function. I think when we studied Fourier sine series, I did this one where L equals 1. So it's not much harder to change 1 into L, and let me just tell you what that is. So if you do that, you get n equals 1 to infinity of 4 times L over n pi quantity cubed. I think this was actually even nicer than when L was 1, because when L was 1, this L went away, and we had a 1 less, or L was pi, and then we had 1 over n cubed pi squared. That was a little bit weird because we have no L's and different exponents, but for general L, this is actually very nice. And then we get 1 minus negative 1 to the n times sine of n pi x over L. So exercise. Verify that this is indeed the Fourier sine series of this function. And please don't continue on until you know that you can do this. So now we have two sine series that we have to set equal. So obviously, Bn has to be equal to this. So we got to equate these two things. And that tells us exactly the missing piece that we need, what Bn is. So now our general solution, or not our general solution, I say our particular solution that satisfies the boundary and initial conditions is u of xt equals the infinite sum from n equals 1 to infinity of 4 times L over n pi cubed times 1 minus negative 1 to the n times sine of n pi x over L times e to the minus cn pi over L squared times t. So we're just plugging this in for Bn here. And that is our final solution. Now let me say a word about what this represents physically. So we have this bar of length L. And at the left endpoint, the temperature is 0. And initially, the temperature is this parabola. So as time goes on, that parabola dies out, like this. And notice that mathematically, this exponential function, this acts like a damper that just kills this sine wave. So each one of these things is going to go to 0 as t goes to infinity. So the limit as t goes to infinity of this function mathematically is clearly equal to 0 because each of these exponential functions kills off the sine wave. And intuitively it's equal to 0 because this bar, if the left endpoints are fixed at 0 degrees, the heat will escape and the bar will eventually become 0 degrees uniformly. So it's always good to check that our mathematics matches our model. And in this case, it does. Here is the summary. Again, the particular solution to the heat equation satisfying the following boundary and initial conditions is this function right here. I'm not going to say it again. I just wrote it out. And what we notice also is that the frequency of the sine wave is just n pi over omega, and the exponent here is cn pi over omega. So in other words, this exponential function kills off sine waves with higher frequency a lot faster, because the larger this exponent is, the quicker this damper goes into effect. So the sine waves in this function, initial condition, that have low frequency gets killed off slowly. In other words, there's a slow decay. But the high frequency waves get killed off a lot quicker. So there's a fast decay. So that's just a fundamental nature of diffusion. And you can go back, if you look at Fourier's law, what that's saying, it says that the larger the gradient is, the quicker the heat or the quantity is going to diffuse. And mathematically, that just means that the more the frequency is, the higher the frequency is, the larger this exponent is, and the faster this exponential function is going to cause it to decay. Okay, that's a great place to stop. What we're going to do next time is we will tweak these boundary conditions. Instead of them being equal to 0, we might make them different temperatures. Or we will do things like, instead of fixing the temperature at 0, we will fix the rate of change of the temperature at 0, and that will represent insulated endpoints. And we're going to leave things right there. See you next time.